Okay, and the last quality of music that I want to talk about is called the quality. And essentially, suppose I had a piano and it was playing a C, and I had a clarinet and that was playing a C. Now, they would both be playing the same frequency, but they're actually going to sound very different. The piano is going to sound nice and clear. The clarinet's going to sound very different. It has some other things going on here. And musicians call this like the color or the tone or the timbre. I'm just going to call it the quality. And it essentially is going to describe everything other than the pitch, the frequency, or the loudness. So let's just talk about what happens when you go ahead and you pluck a string. So here I've got a string, and I go ahead and I pluck this thing. Then what tends to happen is I tend to get vibrations, and those vibrations are going to look like this. And we actually call this the first harmonic. And essentially what we're doing is we are forcing there to be a node right there and a node right there because the string is tied down, so we're not going to have any movement, and we're going to have an antinode right there. Now, whenever you pluck a string, this is the one that happens the most, or pretty much play any instrument. So that guy's going to set up the most. However, what we can also set up is we could set up at what's called a second harmonic, and that still forces the node right there and the node right there. But we can also meet those boundary conditions and have a third node right here in the middle, and we actually call that the second harmonic. It turns out that frequency is going to be double that of the first one. Another way we can meet the boundary condition of a node right there and a node right there is to have two nodes in between, so one right there, probably not surprisingly, we call that the third harmonic, and it's going to be 3 times the fundamental. It's the presence of these partials that's going to determine the quality. A piano is not going to have a lot of those partials. A clarinet will. Now, one thing I do want to kind of keep in mind right here is I want to talk a little bit about the wavelength. Remember, wavelength is one full up and one full down. And so this guy right here is just half of a wavelength. This guy right here is one full wavelength, and that's going to be equal to the length. This guy right here has 3 halves, so it's got one full up, one full down, and then half of one tacked on right there. So here it has 3 halves of a wavelength is equal to the length of this thing. And this guy right here is going to have 1 wavelength and 2 wavelength. And kind of what's going on is the frequencies are correspondingly going up as the wavelength goes down. So let's just get a little bit of practice using these guys right over here. Suppose I have a string and I tell you that it's 0.8 meters long and it has a period of 0.02. So first let's calculate the frequency. The frequency is 1 divided by the period, and so it's going to work its way out to be 50 hertz when you type that into your calculator. Now, the wavelength. If this guy right here is 0.8, then I need to tack on another one. So the wavelength is actually going to be equal to 1.6 meters because I'm doubling that 0.8. And then I'm going to have my good friend V is equal to lambda multiplied by F. And when you type in 1.6 meters multiplied by 50 hertz, what you're going to get is you're going to get a wave speed that's equal to 80 meters per second. Now, how about the second fundamental? The second fundamental is going to have a frequency that is double the fundamental, and so it's going to be equal to 100 hertz. Now, for the second fundamental, we're going to have 1 full up and 1 full down, and so in that case right there, the wavelength is just going to be equal to that 0.8 meters. Now, the wave speed. The wave speed is going to be the wavelength, 0.8, multiplied by that guy right over there. And it turns out that the wave speed is going to also be 80 meters per second. Now, all makes sense in the world because we're not changing the tension, we're not changing the mass. So as the wavelength changes, the frequency is also going to correspondingly change because the wave speed is going to be a property of that string. So that brings us back to quality. How many partials, how many harmonics do we have, and how intense are they? Different instruments are going to have different amounts of them. So let's just take a look at a piano playing a C for a minute versus a clarinet playing a C. You can kind of see that this thing is going to have some fundamental frequency that's going to roughly, be like this. And if you squint your eyes a little bit, you can kind of see that this has roughly the same fundamental, so it's still going to be a C. But the difference is the piano is going to have different number or different amounts of these partials kind of added in here. And when you add in more partials and with higher intensity, then you're going to get different amounts of quality. And it could be a good thing or it could be a bad thing. At the end of the day, how many partials we have and their relative intensity is going to be what allows us to distinguish a C from a piano and a C from a clarinet. So I just want to talk a little bit about musical instruments, and again, when it comes down to quality, they're just all going to be different. I've talked ad nauseum about stringed instruments and how they work. Stringed instruments have a vibrating string. Most of the time it is the fundamental frequency that gets set up, but we are going to have some partials on there as well. We can have a vibrating air column, which is like if you blow on a soda bottle or something like that, you just get some fluttering air that's vibrating back and forth. We have brass instruments, we have woodwinds that have the reed that does the vibrating, but at the end of the day, we have something that is vibrating to produce a musical sound. Now let's talk about a vibrating air column like a flute for a second. Now when I talked about a stringed instrument, what I kind of did was I said, okay, well we have a stringed instrument and this guy is tied down right there and tied down right there, so we have to have nodes right there and nodes right there. When we talk about an air column, what we might have is we might have some air right here and some air right here, and that air is free to move, and so we're actually going to force the exact opposite of nodes. We're actually going to force antinodes right there and right there, and what we're actually going to have is just like this was equal to a half of a wavelength was related to the length of this guy, this is also half of a wavelength, but we're really just forcing the nodes. So half of a wavelength is equal to the length of this thing. The next way to set it up, here we have the fundamental. This would be the first overtone or the second harmonic. Don't ask me why, I didn't make the world, I just try to live in it. And just like with stringed instruments, we're going to say one wavelength is equal to the length, and then we would say 3/2 of a wavelength is equal to the length of this thing. Now, that was an open tube. How about a closed tube? Well, a closed tube, the air right here cannot move. So we actually have to force a node right there as our boundary condition, but the air right here is free to move in and out, and so we're actually going to force an antinode right there. The easiest way to set this up is called the fundamental, and call that the first harmonic, and we would actually just be able to squeeze in 1/4 of a wave, because a wave is one full up and one full down, so if I have a node right here and an antinode right there, you can kind of see that we've set it up right there. Now, vibrating air columns are kind of interesting because we actually only have odd harmonics, and that just has to do with the way that these things are set up. The next thing we're going to set up is we would have a 3/4 of a wave is equal to the length of this thing, called the first overtone, and then we're going to always go up by quarter, so that would be a 5/4 of a wavelength is equal to the length of this thing. Now, I can also talk about percussion instruments like drums and stuff like that, but I'm not going to beat you over the head with them. Essentially, all we have is a two-dimensional membrane, and it's going to act just like a guitar string. How elastic it is going to be related to the tone, and you increase the tension, you're going to increase the frequency, and most of the time we just mess around with the tension of the drum to change the frequency. More tension means higher frequency. So I want to come back and talk a little bit about the quality, and suppose I were to pluck a guitar string that had a fundamental frequency that kind of looks like this. But we did have some second harmonics that were set up, and those guys were probably going to be less intense, so they might look like this. And let's just say, for the sake of an argument, that some third harmonics got set up as well. Well, in order to get the composite wave that comes out of it, pretty much I'm just going to add these guys together and add these guys together and draw a little line right here, and essentially mathematically say that this is going to be the composite wave, and you can kind of see that it's dominated by this frequency right there, and then all of these little dips are going to correspond to all of these little dips, and pretty much the waveform is just going to be the sum of all the sine waves that we have. Now, a mathematician actually realized that we could do this in reverse, and he said pretty much any wave, any periodic wave, could be broken down into sines and cosines of different amplitudes and added together. And if you've ever played around with some editing software, then they actually do something called Fourier analysis, where they go ahead and they do that. What Fourier analysis also kind of says is we can just add various instruments together. So suppose I had an oboe. Oboes tend to have a very large frequency, so a very large guy right over there. If I had played a clarinet, clarinets are going to have a lot more rattiness to them and probably a higher frequency. And if I just went ahead and I added the oboe to the clarinet, then what's going to happen is you can kind of see the oboe is going to dominate, the lower frequencies, and then the clarinet's going to kind of add on top of that. And that's pretty much what Fourier analysis kind of says. So the last thing I want to talk about is how we record musical sounds. And if you recognize one of these old guys right over there, this would actually be called analog music. And if you're into music, then you probably prefer the sound of vinyl. To me, I'm not so picky about it. But something that's interesting about this is this thing only has one groove, and this thing goes up and down as it winds its way around, pretty much on that groove. And analog recording is very different from digital recording. So in analog signal, we have this thing, and it's going up and down in a nice, smooth, continuous function. However, we live in a digital world, and in a digital world, we have ones and we have zeros, and we need to try to represent this analog signal using a digital signal, and we actually do it using the sum of digital signals. So what we kind of try to do is we try to build a little chunk right there that's made of ones and zeros, and another chunk right there of other ones and zeros, and another one right there, and another one right there, and we try to recreate this analog signal. Now, something that's kind of interesting is what do you encode at? Because you can kind of see we're losing stuff here, here, and here. And if I were to encode this, using just one big chunk, then yes, I can kind of capture it, but I'm not going to do a very good job because I'm losing all of this and all this and all this. It's not going to take up a whole lot of hard drive space, but probably not going to do a good job at recreating it. You could also, say I'm going to encode this at a much higher rate, and I'm going to use much smaller chunks, and again of ones and zeros, and I'm going to be able to replicate this signal a whole lot better, but it's going to take up more hard drive space. Now, again, in the real world, when we record this to a DVD or hard drive, we have to do it using ones and zeros. And so we're going to pick off this time right here, and we're going to record the amplitude and recreate that with ones and zeros. At some later time, we're going to pick this time right there, record the amplitude, ones and zeros. Some later time, pick the amplitude, record it with ones and zeros. So what we're essentially doing is we're trying to put a numerical value to the amplitude to try to match this analog signal. And again, how closely we pick those guys together means we can record, we can reproduce it much better, but it's going to take up more space. Now, when you go ahead and you take a quick look at a CD or a DVD, what you're going to see is you're going to see short pits and you're going to see long pits. And the short pits are zeros, the long pits are ones, and essentially what we have to do is we have to add up the amplitude using those ones and zeros. And the way that this thing works is we actually have this laser that goes right there. This thing's going to split it. Some of it's going to go up, get fitted onto the pits. It's going to reflect back. These things are shiny. It's actually going to get recreated right here. And then we have a little detector that says, hey, short pit, long pit, and it's going to add up ones and zeros and try to best reproduce that analog signal.